today's lab is lab number 4. This is a finite state machine. As we can see, the finite state machine has 4 inputs: alpha, beta, reset, and respectively clock, and 3 outputs: delta, gamma, and phi. They're all individual wires, as you can see, and therefore making the entity for this finite state machine called FSM would be a very easy thing to do. Now, looking at the operation of the finite state machine, we have our FSM operation described in this FSM state chart, and we have basically 4 states, as you can see: start, proc1, proc2, and respectively terminal. And then, depending on the various inputs and their combination, we can then move through those states as shown in this diagram. So that is the behavior which we'll need to implement in VHDL. As far as the reset is concerned, reset, as you can see, points to our start state, which is always very important for a finite state machine. So even if a reset is not explicitly shown in the diagram of the machine, here it is, but even if it's not, you always need to add a reset for a finite state machine, because on safety grounds, a finite state machine must always start from a known state when it is powered up. And then when we do the simulation, it's always good for an FSM to do a quick reset to start with, to make sure that the machine always starts from the relevant state. So as far as the finite state machine is concerned, looking at this bubble diagram, we start from the start state and we basically wait there for as long as alpha is 1. We can only move to proc 1 when alpha equals 0. So if alpha equals 0 and we are in the start state, we then move to proc number 1. When we are in proc 1, then we have 2 choices. If alpha is 0, we can then move to the terminal state. Or on the other hand, if both beta is 0 and alpha is 1, then we move into the proc 2 state. So 2 choices there when we are in proc 1 state. Let's say that we are now in the proc 2 state. The only way to move from proc 2 state would be if beta equals 0, and at that point we'll be moving into the terminal state. For any other choice which is different from beta equals 0, we'll be essentially staying in proc 2. So that would be true both for alpha equals 0, as shown in here specifically, but also whenever basically beta is not 0. So if beta is 1, we'll also stay in proc 2 as well. Essentially, the only way to move there would be when beta is 0, in which case we're going to the terminal state. If we are in the terminal state, the only way to move from it would be when beta equal 1. For any other possible input combinations, we'll basically just stay there until beta becomes 1, at which point we'll be going back to the start state. So the operation of the FSM, as described in the bubble diagram, it's fairly straightforward. We have 4 states here and a number of transitions as shown on the diagram. The final thing to consider for this finite state machine is its outputs. They are listed in this table for all the 4 states that this finite state machine can take. So if we are in the start state, delta would be 1, gamma would be 0, phi would be 1. For proc 1, we would have 1, 0, 0. For proc 2, delta would be 1, gamma would be 1, phi would be 1. And then for terminal, we would have delta 1, gamma 1, and phi is 0. So first things first, we need therefore to write the VHDL code to implement this finite state machine. For that, you should really use an enumerated type for the states and the recommended two-process approach for the VHDL implementation. So just refer back to our lecture on finite state machines, which you can also get from the link to the OneDrive I posted. The lecture would be in the lectures folder. Just look at that and to the example which shows how to implement an FSM using two processes. The best approach there would be, again, to write the entity, then in the architecture, create an enumerated type for the states, which would be start, proc1, proc2, and respectively terminal. Then create a current state signal for that. And then in the main code, then process number one would be only dealing with sorting out the asynchronous reset and then generating the next state. The states can be selected using a case statement and then transitions inside of each of those case statements or inside of each of the case branches, rather, those could be basically sorted out using if statements as required. And then the second process, that one will be activated only by the current state. And whenever the first process changes the current state, the second will activate, and that will only set the outputs as detailed in this truth table. So that is logistically how we are meant to implement this finite state machine using the recommended two-process approach. So that's part one of today's lab, writing the VHDL code for the finite state machine using the recommended approach. Part number two would be to basically add a graphical test bench, so not the type of test bench we discussed today, but the traditional graphical test bench, and simulate our code, but making sure that we cover all states and all relevant transitions. So you need to think about how your test bench looks like, because essentially we would need to show all possible operation of this finite state machine. In other words, we would need to look at moving from start into proc1 into terminal and then say back to start, which would be one possible loop into this finite state machine. And then the other possible way would be to go from start to proc1 to proc2, then to terminal, and then to start. So we have two possible loops there, which if we are meant to test this finite state machine extensively, we would need to make sure that we follow. So the test bench and the signals alpha and beta would need to be set in such a way that we show basically the full operation of the machine, both going through the first loop and to the second possible loop as well. And it is always best to test as extensively as possible. So it would be nice to set those signals whenever possible in such a way that basically we stay in a given state for a few clock cycles whenever possible. So bear that one in mind as well when you design your test bench. So that's pretty much it, really. That's what you are expected to do in today's lab. So start by writing the VHDL code for the finite state machine. And then obviously that would entail creating a new project. You can call it lab exercise 4 or lab 4 or whichever way you like. Then create a new VHDL module, call it FSM. Write the VHDL code using the recommended two-process approach as per our lecture on finite state machines. Check for errors. Once you're happy with it, then add a graphical test bench and perform a simulation showing how the design basically goes through the relevant 4 states, and as I said, ideally showing both the smaller possible loop, start proc1 terminal and back to start, and the longer loop, start proc1, proc2 terminal, and then back to start as well. So try to show that sequence, and whenever possible, try to stay in a given state for a few clock cycles as well, just to show that the machine can wait in a state if the relevant transition signal is not active at that point. So that would be essentially the target for today. As usual, I'll give you about an hour or so, and then I'll show you what I've done and discuss basically the outcome of the simulation as well at that point. So let's start by looking at our lecture number 9 on finite state machines. So essentially, as I said, it's slide 27 to 30, which shows the example of a two-process implementation. The skeleton would be, as you can see here on slide 27. So in the definition area of the architecture, we are going to create the new enumerated type and then create the current state of that type. And then we'll have two processes, process 1, which would have the reset and the clock in the sensitivity list. And this one will only deal with the generation of the next state, as well as obviously sorting out the reset. And then the second process will only listen to the current state, because that's the only one in the sensitivity list. And this one basically would then only set the outputs. So that is the skeleton of our program. So if I show you what I've done implementation-wise, here we go. We have our entity setting out the relevant inputs and outputs. And then before the begin of the architecture, here I've set or I've created a new enumerated data type called FSM, and that has the 4 states for our finite state machine, which are start, proc1, proc2, and respectively terminal as well. So those are the only 4 states that we need there. And then I've created a signal current state, which is of the type FSM. So it can only contain as data start, proc1, proc2, and respectively terminal. Once we have that, that's all we need in terms of data definition. So then we can move to process number 1. Process number 1, as we've just seen in our skeleton from lecture 9, contains the reset and the clock in the sensitivity list. It has the reset there because the reset is asynchronous, and because it is asynchronous, we need to basically test that one first. So we'll start with if reset equal 1, then current state would be start. So that points us to the start state. Else if, then we can check for the clock. And then essentially we can use a case statement, which then looks at the current state. And when we are in start, we do something. When we are in proc1, something else, and so on, depending on what the diagram shows us. So when we are in the start state, if we're looking at the diagram, we are now here. What we need to do basically is to wait there until alpha becomes 0. And when alpha is 0, then change the state to proc1 instead. So let's see if that's what's happening. See, if alpha equals 0, then current state becomes proc1, and if. That's it. We don't need to have an else or anything else, because essentially if we don't move, then we stay there. And the only way to move is to say if alpha equals 0, then current state is proc1, and that's it. So that's the simplest way in which we can deal with the transitions when we are in the start state. When we are in proc1, so let's see what's happening there. Now we are in proc1. We have 2 possibilities here. If alpha is 0, we need to move to terminal. Otherwise, we need to check for beta equals 0 and alpha 1. And when that is the case, we can move to proc2 instead. So let's see how the code looks like. It says if alpha equals 0, then current state equal terminal. So we move to terminal when alpha is 0. Else if, We check then the second condition, else if beta equals 0 and alpha equal 1, then current state would go to proc2, and if. Again, that's it. We don't need anything else there. When we are in proc1, the only way to go from there would be either on this branch to terminal or via that branch to proc2, and that's proc1 sorted. So if we then move to proc2, in proc2, the only way to move out of it would be for beta to be equal to 0. So if we go to the code and we look at when proc2, there we only need to say if beta equals 0, then current state is terminal, and if. That's it. That's the only way to move to terminal. Otherwise, we just stay there. Remember, in VHDL, everything inside of a process is static. So basically, everything is remembered, and unless you change it, it just stays where it is. So that's basically pretty much when we are in proc2. And then finally, the last state we're interested is terminal. And when we are in terminal, the only way to move there is when beta is 1, and then we go to start. So from terminal to start with beta equal 1. So if we look at the code, it says if beta equal 1, then current state is start, and if. And then we end the case, and then we end the main if-else if, and we end the process. So that's basically the first process, setting all the states based on the relevant transitions and dealing with the reset. So that's the only job of the first process. Now moving to the process number 2, that one has a unique label P2, and now only listens to the current state. And what we have here, again, we can use a case based on the current state, and then the branches would be start, proc1, proc2, and terminal, just like before. But this time, we only need to set the outputs as shown in the truth table. So we need to basically set, when we are in the start state, set delta 1, gamma 0, phi 1. In proc1 is 1, 0, 0, then 1, 1, 1, and then 1, 1, 0. So those would be then the outputs corresponding to the relevant states. And that's exactly what's happening here. So you can see that in the start state, we set delta to 1, gamma to 0, phi to 1. In proc1, we set them again as they are in the table, and so on. So the second process basically only deals with changing the outputs whenever the current state changes. The way these two processes work is that as soon as process number 1, when the clock arrives or when a reset arrives, changes the state, because current state changes and the two processes run in parallel, the second process, which is sensitive to a change in current state, would trigger an event, and then we go in and change the values depending on which state we are in. So that's basically the way it works. So that's pretty much the VHDL code, pretty much sorted out, fairly straightforward. Really, all we need to do is to look at the relevant output values and then follow the relevant states and transitions shown in the finite state machine diagram. So that's writing the VHDL code. Then, of course, we need to add a test bench to it. Now, the test bench ought to show our state transitions according to the finite state machine diagram. So let's see how we can show comprehensively what's happening here. So if you look at my test bench, here is what I've done. The most important thing really, as always, is to start with a brief reset to make sure that we put the machine in the relevant state. So while that reset is active, because the reset is essentially asynchronous, you don't really care about the clock, the machine at that point will be put in the start state. So we would be there, and that would be the effect of the reset. And then if we want to move from that start state, we would need to be setting alpha equals 0. Now you see that what I've done here is at the same time put alpha in 1, which basically keeps me in the start state for a few clocks. And then I waited a couple of clocks and then put start state in 0. Alpha in 0. So if alpha is 0, looking at the diagram, then I can move from start state into proc 1. And then depending on what the values of alpha and beta are, I can go either to terminal or proc 2, but that would be the next step. So the first step is here, where basically I set the value of alpha to 0, and at that point the machine will move into the next state, which is proc 1. So now I'm in proc 1. Alpha is now put back to 1. And at the same time, I've basically put, before the next clock arrives, that is, I've put beta in 1. So alpha is 1 and beta is 1. Let's see what that means. Alpha 1, beta 1 means that since alpha is 1, I can't go to this branch. And since beta is 1, even though alpha is 1, I can't go on that branch. I can only move basically from proc 1 if either beta is 0 and alpha is 1, or if alpha is 0. But since my alpha is 1 and my beta is 1, I can't go either this way or that way. So I'll stay there basically for as long as those inputs are still in force. So for as long as basically I've got 1 for alpha and 1 for beta, I keep the state and I stay basically in proc 1. Then I make beta to be equal to 0 and alpha stays in 1. If beta is 0, and alpha is 1, then I'll be going this way because this condition is now true. I'll go from proc 1 to proc 2. Okay, and then in order for me to stay in proc 2, I would need to change that beta from 0 to 1 at the next opportunity before the clock arrives. Because if beta is 1, then I won't be able to go to terminal and I'll stay there for a few clocks. And that's my intention. So if I go to the simulation and look at what I've got here, I've got basically that beta 1 that alpha 1 and then put beta back to 1 immediately, which means that both of them are 1 and I can't move. I'll stay for the entire duration there into our proc 2 state. And then I'm going to change beta to 1, which will allow me to move from proc 2 to terminal. And that happens essentially here, where I'm going to change my beta to 0. Alpha is 1, but because essentially beta is 0, at that point I can move to terminal. And I'll be stuck in terminal because I can only move from there if beta is 1. And at the moment my beta would be 0. So if you look at what's happening there, during that period where beta is 0, I'll be stuck essentially in our terminal state. And then a few clocks after, I'll turn beta to 1, which will allow me to go back to the start state. And that happens here. As you can see, I put beta to 1, which takes me back to the start state. So at that point, I'm in the start state and beta is 1 and alpha is 1. So what's going to happen there is, here we go. So I'm in the start state and alpha is 1, beta is 1. Because alpha is 1, I'll be stuck in the start state until I change alpha back to 0. So that happens basically here. Alpha goes back to 0 and then immediately back to 1 because I want to stay in the next state for a while. So as soon as that alpha goes to 0, then I'll be moving to our proc 1 state. And then because alpha becomes 1 again and beta is not 0, I'll basically be stuck again for a while in proc 1. So that's what's happening here. Because my beta is 1 and alpha is 1, during that period of time, I expect to stay in proc 1. Then I change alpha to 0 and beta to 0. So let's see what's happening there. So now I put beta to 0 and alpha 0. Beta 0 would be okay partly for this transition, but because I set alpha to 0, then this condition would be false, so I won't be able to go there. But because alpha is 0, I'll be able to move at that point from proc1 to terminal. And because my beta is set to 0, I'll be stuck in terminal until I change it later on to 1, which will then take me back to start. So taking it step by step, here, because I've got alpha 0, beta 0, I'll be staying essentially in the terminal state. And then as soon as I change beta to 1, that will take me back to the start state. So change beta to 1. Once I'm in terminal, that will take me to start state. And at that point, depending on what the value of alpha is, I can either move or stay there. So let's see what's happening. If I'm now in this position, because alpha is 0, it will allow me then to move to the next state, and then depending on the values that are set, we can do some other state changes there. The last thing that I've done here is to have an extended reset period just to see the reset operating during a couple of clock cycles to show its asynchronous nature. So I've basically enabled reset there, and I kept it enabled for a bunch of clocks just to see it working. So that's pretty much my test bench and the reason why those signals were set like that. So you always have to think how those signals are set and to aim to stay whenever possible in a state for few clocks to show that when a transition is not met, then you are maintaining that state. And remember what we discussed earlier today in the lecture. Basically, things are happening or are changing at the beginning of the blue period, so that is before the clock arrives. So by the time the clock arrives, which is at the end of the blue period, then the signal is already settled and it will read the new value. So with that in mind, select the test bench and then expand in the processes window the simulator and double click on simulate behavioral model. And that will basically show us the simulation waveform, which is this one here. So looking at what we have, at this point, my reset goes high, so I'm resetting, which means that my state of the machine is, as you can see in here, gamma is 1. Sorry, delta is 1, gamma is 0, and phi is 1. So if we're looking at the table, delta 1, gamma 0, phi 1 corresponds to the start state. So as expected, the reset puts us in the start state. So up to that point, at least, we'll be in the start state. When the next clock arrives, because my alpha signal is in 1, nothing changes. So I'm now here. Alpha is 1, so this condition is not met. Therefore, I'll stay in the start state, as I've just explained earlier. Then I change alpha here, just before the clock arrives. I put it to 0. So when the next clock arrives, it will read alpha equals 0, and that basically will change the state from start to proc 1. So the next state would correspond to proc 1, which would mean delta 1, gamma 0, and phi 0. So phi should change from 1 to 0, indicating that we are now in proc 1. And looking at what's happening, indeed, you can see here that phi is changing at that point when the clock arrives back from 1 to 0. So now the new combination of outputs is 1, 0, 0, which corresponds to proc 2. Because I want to stay in proc 2, at that point, which is just before the clock arrives, I put both alpha and beta into 1. And because they're both 1, looking at the diagram, when I'm in proc 1 and alpha is 1, I can't go that way. And when beta is 1, obviously I can't go that way. So I'll be stuck in proc 1 until either alpha or beta changes to satisfy one of the two conditions. So looking at what we have here, Then beta is put in 0 few clocks later, and then as soon as the clock arrives, you notice that the state changes now because beta is 0 and alpha is 1, and the state changes to 1, 1, 1. 1, 1, 1, if we're looking at the truth table, corresponds to proc 2. So let's see if that's right. Because now beta is 0 and alpha is 1, we are going to proc 2, which is correct. So if we go and have a look, at that point, basically beta was 0, alpha 1, which changed the state immediately to proc 2. And then before the next clock arrives, so the machine has an opportunity to change the state, I put beta back to 1, so alpha is 1, beta is 1. Therefore, I'll be stuck in that proc 2 state for a while, because if we look at the diagram, if I'm in proc 2 and beta is 1, I can't move from there. I can only move when beta is now set back to 0. So I'll stay there for few clocks, and then I put beta back to 0 here, and then as soon as the clock arrives, now my output state changes from 111 to 110. 110, if I look at the truth table, now corresponds to terminal. So now basically I've moved to terminal exactly as expected because beta was set to 0. And if I want to stay in terminal, I need to set that beta back to, or I need to keep that beta in 0, in fact, so I can't move when the next clock arrives, which is what I'm doing if you have a look. So basically I'm keeping beta in 0, which means that at least up to this point, I'll stay in the terminal state. At that point, I'm changing beta to 1, which will allow me to move when the next clock arrives there. And you see that the new state changes to 1, 0, 1. So if I go to the diagram, 1, 0, 1 now corresponds to the start state. So basically, because beta was 1, I moved from terminal to start. So now I'm back to start. And if I ensure that alpha is 0 at that point, I can stay in start for a while. And here you can see that what is basically happening is I keep that state for a while, and then as soon as I've got my alpha in 0, I can then move and change state to 1, 0, 0. And if I look at what 1, 0, 0 corresponds to, 1, 0, 0 now corresponds to proc 1. So as soon as alpha was made 0, I can move from start to proc 1. And then if I now want to go on this route instead, I can basically put alpha in 1 and beta in 1 to stay there for a while, and then I can change alpha to 0, which will then allow me to move from proc 1 to terminal. So let's see what's happening here. To stay there for a while, just before the next clock arrives, I make sure to put alpha in 1, beta it's already in 1, which means that I'm now in 1, 1. 1, 1 means I can't go either this way or that way, so I'm stuck in proc 1. And then a few clocks after, I'm going to set alpha 0, so I can move to terminal. So you can see that after a few clocks, I now set both alpha and beta to 0, which will allow me then to change the state when the next clock arrives, and essentially then move into the 1, 1, 0 state. 1, 1, 0, if we look at the table, corresponds to terminal. So now basically, because alpha is 0, I move to the terminal state. Beta was also 0, but because my alpha is 0, that condition was false. So only this condition was true, hence why I moved from proc 1 to terminal. And then if I want to stay there, because beta is 0, I'll stay there for a while. That's why I set it to 0 there. So I'll keep that state until such time that beta is now turned to 1, just before the clock arrives. As soon as the clock arrives and finds that beta is 1, it will then change the state to 1, 0, 1. So looking at what 1, 0, 1 corresponds to, that is the start state. So then I'm going back to the start state. Okay. At that point, alpha is, as you can see, 0, which means that when the next clock arrives, it will change state. and then it will go to proc 1. So here, then in fact alpha remains in 0, and because that is the case, it will then move on the next clock to terminal. And you can see that happening here on the next rising edge, because alpha continues to be 0, will be moving to terminal. Then because alpha is still set to 0, will be then on the next clock move from start to proc 1 again. And you can see that here. So on the next rising edge, we now move to terminal again. And because alpha is still 0, it will then move to terminal on the next clock. So it will keep doing that loop for as long as that alpha 0 continues. So here on the next rising edge of the clock, I'm moving to terminal again. And then you notice that at that point here, reset goes back to 1. So then the state changes immediately without waiting for the clock. Hence the behavior is asynchronous. And that changes to 1, 0, 1. And 1, 0, 1, if we're looking at the table, corresponds to start. So basically the reset, for as long as reset is active, will be stuck in the start state. And then once reset is disabled, then because alpha remains in 0, I think, we'll be then doing that loop again and again. But that would only happen from this point onwards. So there you go. That's pretty much then the simulation matching the expectation that has been set as part of our test bench. And again, as I said earlier, if you're still on the default color scheme, the black color scheme, you can always go to Edit, Preferences, and then ISE Simulator, expand it, Waveform Colors, and then make sure you set here from default to Classic. And then it will show you your simulation like it's showing mine here on the light color scheme. So that's pretty much it for today's labs, folks.